ladies and gentlemen. Welcome to Physics 20 Kinematics, Lesson 4, Graphical Analysis, Part 1. So today we're going to do quite a few things. We're going to analyze data and apply mathematical and conceptual models to develop and assess possible solutions. We're going to construct graphs to demonstrate the relationships among displacement, velocity, acceleration, and time for uniform and uniformly accelerated motion. We're going to analyze a graph of empirical data to infer the mathematical relationships among displacement, velocity, acceleration, and time for uniform and uniformly accelerated motion. And we're going to relate acceleration to the slope of and displacement to the area under a velocity time graph. Now, by looking carefully at the displacement versus time graphs, we can determine what the corresponding velocity versus time graph and acceleration versus time graph is. So, my apology, there's a typo here. This is supposed to be displacement versus time, and this is acceleration. My apologies, but we'll fix that later. So we have a displacement time graph. We can turn that into a velocity versus time graph, turn that into acceleration versus time graph. Now, big shot mathematicians like Maxwell call this taking derivatives. You'll just be calling it the good times. Yes, wait till we get to calculus. Anyway, now, here, every graph tells a story. Now, there are three types of graphs you'll deal with in kinematics. Distance versus time. Sorry, actually, displacement, my apologies. Velocity versus time. And acceleration versus time. Displacement versus time. My bad. Now, each one of these situations can have a number of different cases attached. So pay attention. Case 1, no movement. So there's your displacement versus time graph. The object is sitting still. Notice there is no velocity versus time graph and no acceleration versus time. Now, technically, we could say, but Mr. Sutton, it has zero velocity. And it has zero velocity, zero acceleration. Yeah, we prefer to say no graph. Now, you're right. We can write a graph with zero velocity. Now, here, stress uniform motion, zero velocity, zero acceleration, and the distance does not change with respect to time. Because it's uniform motion, you're not moving. Case 2, constant velocity, positive. And notice here the displacement versus time graph is going up at a constant rate. The slope of that line will be your velocity, which is whatever this number is. And the slope of the velocity line is 0. So there would be no graph here. You could draw a line at time is 0, at acceleration equals 0, but generally we just don't draw the graph. Now here, uniform motion is positive direction, or up or right or east, whatever. Now we can use velocity, and poopy, I forgot the arrows. Displacement over time. We have zero acceleration. And we can find the slope of the distance versus time graph gives velocity. All right? Now, case 3, constant velocity in the negative direction. Notice here displacement versus time is going down, which means you're going negative velocity, so you have a negative number down here. And note that that's flat, so there's no acceleration graph. Now, be specific. Uniform motion, negative direction, down, left, west. We can use velocity as displacement over time. I forgot my arrows again. Zero acceleration. Not speeding up, not slowing down. Find the slope of a distance versus time graph gives velocity once again. My apologies, I can't read my own typing. Now, case 4, constant acceleration positive. You speed up. Now notice with the displacement versus time graph, it's curved going up. The slope of that is constantly changing. Save that calculus. I'll explain how to solve for that. But for the moment, realize the velocity is increasing a certain amount. Time, changing velocity. That slope gives us acceleration, some number. Okay? So here we have changing velocity. And we have to use the kinematics equations. Velocity final is velocity initial plus at, displacement is v initial t, those ones. Now, We have positive acceleration. Now the acceleration is the same direction as velocity. Sorry. Now, it means we speed up. This would be like dropping a water balloon off the gym. It speeds up. Now, finding the slope of a velocity versus time graph gives us acceleration. Now, fifth case, constant acceleration, negative. Notice what happens with the displacement versus time graph. It's going down curved, not straight. Finding the slope of that is beyond our ability. We can do, I'll explain it in calculus. For the moment, trust me when I say it's a constant velocity. And since the slope of the velocity time graph is 0, there's no acceleration. So this is changing velocity. We must again use kinematics equations. And this is, oh God, help me, negative acceleration. Acceleration in the opposite direction is velocity. We're slowing down. Finding the slope of a velocity versus time graph gives acceleration. Now, graphical, and sorry, those are the 5 versions you have to know. So keep those notes handy. Now, going on to graphical analysis. One of the most difficult skills in Physics 20 is the converting of raw data into graphs and the interpretation of these graphs. However, these graphs are a powerful tool which allow us to communicate physical phenomena and make inferences into the laws of nature. To recap, slope of a distance versus time graph gives a velocity. Displacement. Why am I saying distance? Slope of acceleration versus time, slope of velocity. I apologize, ladies and gentlemen. Versus time graph gives us acceleration. Area under velocity versus time graph gives us displacement. And the slope, remember the different versions, y2 minus y1 over x2 minus x1, d2 minus d1, t2 minus t1, change in velocity. Now remember, if we're doing change in velocity, that's v2 minus v1 over t2 minus t1, which is acceleration. Sorry, change in velocity over change in time, I should say. That gives us acceleration. Now, investigation red versus blue runner. So this is a gizmo. I'm going to put this as a separate link in the Google Classroom. I want you guys, if you're not in school, I want you to play with it at home on your computer. If you're in class, I'll be giving you time to play with it, and you can see displacement time and velocity time graphs. Actually kind of nice. Anyway, I'm actually going to pause the recording here. Yep. So those of you at home, you go to the link in the Google Classroom and play with it for a little while. All right? Then we'll come back and talk. Good luck.